Hey guys, today I'll be explaining the physics quiz for week 5, term 2. Alright, so let's begin. Question 1. Which of the following factors affect air resistance acting on an object? Select all that apply. Alright, so for this question, they want us to choose the factors that affect air resistance. Alright, so let's look at the first one. The relative speed of the object with respect to air. So relative speed of the object with respect to air. So have you ever been, of course you've been, like when you're in a car and you're opening the window and you're going at very high speeds. The wind hits you a lot, it's really strong, and you put your hand outside and it's really nice. So that amount of air, it's the air resistance trying to stop the car. So as the faster you go, the stronger the air resistance will be. The slower you go, the weaker air resistance will be. Alright? With the weaker air resistance. So you got that? So again, faster you go, stronger air resistance. Slower you go, weaker air resistance. That's it. Okay, now for the second one, surface area of the object. Now let's imagine a guy with a parachute. Okay, a skydiver with a parachute. Now the parachute, whenever you see a movie or the news, when you see skydivers, the parachute is always really big. The way that it's so big, like this, and it's like this. Okay, so when it's big like that and wide, not only long but also wide, it affects the surface area. So that way, a lot of air resistance can affect it. So the skydiver can slow down. So the more surface area it has, the more air resistance it will have. So he will go slower. That's why they use parachutes, so they don't fall to their death. No, they use parachutes so it slows them down. That's it. The shape of the object. Now let's compare a normal car you see every day, Toyota or whatever, with a racing car. I know I'm very bad at drawing, but bear with me. Okay. A racing car. This is the racing car, and this is let's say Toyota. Okay. Toyota. So Toyota is is wider, but the racing car is longer and has it's less wide basically and longer. That way, it less air resistance will affect it, and it will go even faster. That's why racing cars are way faster than the Toyota cars or whatever cars you use, Jeep or whatever. They're just normal cars that have a relative speed, a good speed, but racing cars are specifically built like this to race and be really fast. That's why shape of the object matters. Alright? That's it. Density, of course not, and temperature doesn't even have to do anything with this. Alright, for this question, describe the motion of the skydiver in a chronological order. Label the first step as 1. Okay. 1 minute. Okay. So the first step, the skydiver jumps from the airplane without opening his parachute. Now, okay, of course, how do people skydive? The plane, there's this plane that there's a plane that takes them all the way up in the air. All the way up in the air until they reach a specific height, and then the skydiver opens the door and jumps out. Like this. Okay. Now they won't open the parachute right away, because they have to go down a specific height, then they open the parachute. because where's the fun in that, right? So they skydive, they fall for a bit. Let's see the second step. Okay, the skydiver speeds up until he reaches terminal velocity. Okay, so the skydiver will accelerate until he reaches terminal velocity. So what is terminal velocity? Is when a body reaches what's it called? Maximum speed. So it can't accelerate anymore, and it's like the maximum speed. It will stay constant. So when it reaches maximum speed, we can call it terminal velocity. So now the skydiver will accelerate, as I said, and it will reach terminal velocity at a specific height. Alright? So yeah, he will reach the terminal velocity, and then third step, the skydiver opens his parachute and starts slowing down. Now, after reaching terminal velocity and reaches a certain height, the skydiver will open his parachute and slow down, because from the last question, air resistance, because the parachute is wide and it's big, more surface area. So the air resistance will slow the skydiver down. Now for the final step, once we erase all of this. Final step, the skydiver's speed decreases until he reaches terminal velocity. Now his speed will decrease until he can't. His speed is like what's it called? Until he can't decrease anymore. Like same thing, we say he can't accelerate even more, he can't decelerate even more. So there's two cases of terminal velocity. When you reach maximum speed, and maximum speed even when you're like slowing down. Maximum speed is when your terminal velocity, how do I explain this? Let's say the skydiver now, خلاص, he reaches the ground. Now he has terminal velocity. Now he can't decelerate even more. Now he's at rest. That's it. Okay, for next question. The moon orbits Earth in a roughly circular path as shown. What force is responsible for the moon's circular motion? Choose the correct answer. Alright, so obviously it's the gravitational force that keeps the moon in the orbit. Well, yeah, it's Earth's gravitational force. So, let's say the satellite. A long time ago, we shot the satellite up from Earth until it reaches here. Now, satellite, we can call it a moon of some sort. It's when an object, not just a satellite, an object comes from a really, really high speed and then ends up here. Now, when it's here, the gravitational force will start acting on it, and it will stay stuck in the circular motion forever. Same as the moon. The moon's always been there. It's there for it's still there and will forever be there because of the gravitational force. That's it. And now for the second one, what can be said about the direction of this force? Well, yes, it is perpendicular to the moon's orbit. Direction of the force is over here. 1 minute. Over here. Like, I think it's over here or over here. Anyways, it's perpendicular to the moon because it's a straight line like this. So, 1 minute, which there is. The force acting on it is from Earth's gravitational force, right? So the force will be from here. That's it. This is perpendicular to the moon. That's why it's stuck in that orbit, because of the gravitational force. Alright, that's it. Question 4. In an experiment, different loads are applied to a spring. The results of the experiment are shown below. Okay, now let me just tell you a rule you have to memorize. Oops. A rule you have to memorize. It's called Hooke's law. Now, Hooke's law is F, which is force, equals K delta L. Now, let me tell you what each letter represents. F is the force. K is the spring constant. You only use this when you want to find when it's related to elastic objects. And L is delta L is what's called the extension. the distance يعني. Okay, so now let's see. They want us to find the spring constant, which is K. This. And we're given the force and the extension, which is L. Now that we're given these two variables, we can easily find K, which is the spring constant. Now for K, since F and the force and extension are not are directly proportional, we put F over L. Okay, so we divide the force by the extension. Now the force we have is 10. Let's take this point. We can take any point, but I'll take this one. This point. The force here is 10, and the extension is 0.20 meter. Make sure it's always in meter. Okay. Now we put 10 over 0.2 is 50. And yeah, it's 50. That's it. It's easy. So always remember to use the rule F equals K delta L. So you'll be using this throughout this exam. Okay. For question 5, a satellite is an object drifting in space around the planet. Which force makes a satellite orbit around the planet? Since the gravitational force is acting on it, it has to have a weight, right? So the reason it's not falling out of orbit is from the gravity from the Earth and its weight. Since if it doesn't have weight, gravity can't affect it. And of course, everything has weight. Well, except some stuff in space, but we won't talk about that now. According to Newton's first law, what would be the trajectory of satellite if no force is acting on it? Okay, a straight line. Now, why? Because first, what does Newton's first law state? Newton's first law: an object at rest remains at rest, or if in motion, remains in motion at a constant velocity, unless acted on by a net external force. Now, since since in this case there is no force acting on it, it will be in a straight line. Why? Because it doesn't only affect if it's remain at rest. If it's in motion, it will stay in uniform rectilinear motion if no force acts on it. So it will stay constant and in a straight line. Straight line, same direction, same speed. That's it. If no force acts on it. Alright, that's it. Astronauts inside the space station feel weightless. Well, yes, they feel weightless because they are in free fall. Of course, they feel weightless. You've seen those movies when You've seen those movies when the astronauts are in like a space station or a spaceship, and they float, right? They're not standing upright. They're like floating around anywhere, not in a specific direction, just floating as if there's no gravity. So of course they would feel weightless, like they don't have weight because they don't feel gravity. No gravity, no weight, right? That's what they feel. But of course their weight is still there. It's just there's no gravity. That's it. Which statements about terminal velocity are true? Okay, it is the velocity acquired when the net force on the body becomes zero. Okay, let me write this for you. Okay, when net force becomes zero, what can you remember? That acceleration is zero, right? And when acceleration is zero, we achieve terminal velocity. Okay? So no acceleration means we achieve terminal velocity when we are maximum speed and constantly moving. Okay? Now for the second one, it is related to air resistance that increases with speed. It is related to air resistance that increases with speed. Yeah. Okay. So now let's imagine a skydiver falling. All right. Like I said before, they're accelerating, and what makes the skydiver like stop accelerating? If there's no force, they would be accelerating endlessly. But since there is a force acting on the skydiver, one of the forces is air resistance. All right, this air resistance is opposite to the acceleration, so it defies it. So that's why he slows down until he reaches terminal velocity, which is the same speed. So it is related to air resistance that increases with speed. So, like I said before, when speed increases, air resistance increases. That's it. And for the last one, it is a constant velocity. Like I said before, when terminal velocity is achieved, it is maximum speed of a body, and it moves constantly. It has a constant velocity. That's it. Make sure to memorize this, alright? Alright, question 8. When a material goes back to its original shape after a force is removed, the material is said to be elastic. Take a rubber band. When you stretch it, and then you let go, it will return back to its circular shape. That's it. Okay. The extension graph for a copper wire is shown below. Match each letter on the graph to its corresponding description. Alright. Let me just write this for you so you can understand more. For A, let's take A first one. A is Hooke's law obeyed. Now let's see where A is. This is A. Alright? This whole thing is A. It's when you stretch something and it extends, right? Like any elastic object there is, it's extending and that's it, okay? So it's obeying Hooke's law. Alright? Which is if you apply more force, the more it will extend. For B is elastic limit. Now, one minute, let me just erase this. Okay, for B is elastic limit. Now, elastic limit here is B. Now, this elastic limit is when the elastic object can't extend even more. So as a rubber band, it's like this, right? You will try to stretch it until you can't even anymore. It will become like this. Like this. You can't stretch it even anymore, and then you let go, it returns back. So that's the elastic limit. Alright? Okay, for part C, 1 minute. For part C, it's plastic behavior. Okay. So now when we extend it past its elastic limit, it will obey the behavior of a plastic. And what's which is this is C. What's the behavior of plastic? Take a plastic bottle, for example. You squish it, which is basically like, or stretch it. When you do that, it's now deformed forever. Like, you can't return it back to its original state. And even if you try, it will look smudgy, right? Like if you crush a plastic bottle, if you crush it, it will look like this. Alright. Right? It will look like this. Now if you try to like a bit widen it and fix it, it will still look smudged. It will look like this. It will look smudged. Okay. Sorry about that. That was a phone call. Anyways, for part C, plastic behavior. Yeah, as I was saying, when you plastic behavior basically means when you stretch an object and it becomes deformed. So you can't return it back to its original state. So that's what's happening here. When you stretch it past its elastic limit, it will begin to deform. All right. For part D, the last one, permanent extension. Now, when you stretch it even more past the plastic behavior over here, now you can't return it back at all. It's impossible. Now this is called permanent extension, where you extend it and now you can't return it back to the original shape. Now it's not considered elastic. Okay, so that's it. Okay, for question 10, as long as the elastic limit of a spring is not reached, the expression F, known as, F equals K delta L is Hooke's law, can be applied. When a force of 50, before I do anything, as long as the elastic limit of a spring is not reached, this applies before the elastic limit, right? Okay, so when you extend it, as long as it doesn't reach elastic limit, Hooke's law can be applied. Okay, that's what they're trying to say here. Now, when a force of 50 Newton is applied on a string in elastic limit, it elongates by 25 centimeter. For this spring, the spring constant is K is 200, Newton per meter. Okay. Now, for this one, we're gonna use Hooke's law, which is F equals K delta L. Let's see what we're given. We're given force, which is 50 Newton. Let's see, but 50 equals, we're given L, which is 25 centimeter, but be careful. When the extension L is always in meters, so we have to turn from centimeter to meter. And to do that, we just have to divide by 100. So 25 divided by 100 is 0.25. Yep, it's 0.25. Okay, now we can use the rule. We're trying to find the spring constant, which is K. So K, and then we have 0.25 here. 25 here. Okay, so now since force and extension are directly proportional, we can divide them. 50 divided by 0.25, it will be equal to 200. And that's it. That's the spring constant, 200. Right? That's it. Question 11. A material that stays permanently deformed after a force is removed is said to be plastic. Like I said, the plastic bottle, when you squish it, when you when you crush it and it becomes deformed, you can return it. You can try to fix it, but it will look smudgy, so it's forever deformed. For part B, a material which can be made into very thin wires without breaking is said to be ductile. Metal is an example. You can make it into very thin wires, but without breaking it. That's ductile. Remember, the properties of metal is one of them is ductile. Okay. For C, a material that breaks suddenly just after its elastic limit is said to be brittle. Okay. So let's take example glass, eggshell. Those materials are considered brittle because when you apply force to them, they break. All right. So when you try to stretch it past its elastic limit, it breaks immediately. Unlike rubber band and stuff like that. All right. For part D, a material that does not stretch or bend is said to be stiff. Now, let's say, what's an example? I assume rock. You can't stretch rock. Yeah, you can't stretch rocks. If you try to stretch it, it will break. Alright? That's it. Wait, no. 1 minute. I don't have any examples right now, but if it does not stretch or bend, it's called stiff. That's it. Like, you can't stretch it or bend it. Underline the quantity that can be measured by a spring balance. Spring balance is used to measure force, of course. That's known. Just memorize this. Memorize that spring balance is a apparatus that's used to measure force. Students are measuring how the extension of a spring varies with the force applied to it. The results are summarized in the table below. Okay, look. The law that this experiment supports is called Hooke's law. Okay, look. We have force, we have extension. We can immediately deduce that it's Hooke's law. Okay? Now for the second one, the spring constant of the spring tested by students is, okay, they want the spring constant. We'll use Hooke's law, which is force equals K times delta L. Now we're trying to find, again, the spring constant, which is K. So we're gonna do F over L. Okay? Delta L, sorry. Now we're given the force in L. L is extension again. Here's force, here's extension. We can take any of them, except the first one, since there's nothing here, there's no force or extension. We can use any of them. I'll take the last one, 10 and 40. Okay. Now before we apply it, we have to turn millimeter back into meter, since extension has to be in meter. Always look out for this, guys, because one simple mistake such as this can sacrifice your whole mark. Okay? So from millimeter to meter, you just have to divide by 1K, which is 1000. So 40 divided by 1000 is 0.04. 0.04. Okay? And the force is 10. So force is 10 over the extension, which is 0.04. 10 over 0.04 is, let me check, 10 divided by 0.04 is 250. And yes, indeed, it is 250. That's it. That's it. Question 14. A student is making a spring balance using a spring balance. Using a spring with an arrow and an ordinary ruler, she wants the existing marks on the ruler to correspond to the force applied to the spring balance in newtons. The ruler is originally graduated in centimeters. Okay, the student should use a spring constant. Okay. For this one, wait. Yeah, for this one, it's originally measured in centimeter, right? And at the same time, it's measures Newton, which is force. So it can measure both centimeter and the Newton. Alright, and they want the spring constant. We can use Hooke's law, F equals K delta L, to find the spring constant. Now we'll say, where's the force? Where's the extension? They're right here. Both right here. We can take any point. Let's take 3, for example. This is 3 centimeter. At the same time, it is 3 Newton. We have force, but we don't have extension because it's in centimeter. We have to turn it from centimeter to meter. And to do that, we divide by 100. So 3 divided by 100 is 0.03. Okay. So now we have force as 3 and extension as 0.03. Since force and extension are directly proportional, we can divide them. 3 over 0.03 is equal to 100. So that's it. That's a spring constant, and yes, indeed, it is 100. Okay, a 60 kilogram skydiver is free falling in mid-air. After a certain interval of time, he reaches a constant speed. Okay, like I said before, when the skydiver stops accelerating and reaches constant speed or constant velocity, that is called terminal velocity. Okay? First one, what is the term used to represent the speed that the skydiver reached? It's called terminal velocity. It's when a skydiver reaches maximum speed dash constant speed. Alright? For part B, what is the net force acting on the skydiver once he reaches that speed? Now, in terminal velocity, there is 0 Newton acting on it. 0 net force. Because if an object is moving at constant speed, then there is 0 Newton. Alright, which follows Newton's first law. Which follows Newton's first law. An object at rest remains at rest, or if in motion, remains in motion at a constant velocity, unless acted on by a net external force. So yeah, it will stay in motion unless a force acted on it. So since the skyriver is in constant speed, so there is no force acting on it. So it's 0 Newton. So for last one, what is the magnitude of air resistance in the moment of time? At that moment of time. Okay, we can use F equals ma to find this. They want force. We're given mass and acceleration. Mass is 60 kilogram and acceleration is 10 meter per second squared. Look, guys, I want to tell you something. You're gonna say this is the G, the given one. So how the acceleration? This is called the gravitational acceleration. So if we're not given any acceleration, we can use the gravitational acceleration, the 10 meter per second. All right. So since this is also considered acceleration, we can also substitute it for acceleration. So that's why it's we're substituting it here. So 60 times 10 is 600. Okay, so the force is equals to 600, and indeed it is 600 Newton. That's it. For question 16, David has a spring of unstretched length 5 cm. When he hangs a weight of 20 Newton from one end of the spring, its length becomes 15 cm. The value of the spring constant is 200. Again, they want us to find the spring constant, which is F equals... F equals K delta L. Okay? We're given the force, which is 220 Newton. Now, for the extension, we're given 2, right? No, that's not extension, that's just the length. The extension is how much it's extended from its original length. So we don't count the original length. So we just subtract 15 minus 5. 15 minus 5 is 10. The extension is 10. It extended 10 centimeter from its original length. So the extension is 10. But wait, before we apply it, it's in centimeter. We have to make it from centimeter to meter. Divide by 100. So 10 divided by 100 is 0.01. Wait, no, sorry. It's 0.1. Okay? Since moving from here 1, 2, it's going to be 0.1. Okay? So it's 0.1 meter. We can make it, since we want the spring constant, we can divide the force by the extension. The force is 20, the extension is 0.1. 20 divided by 0.1 is 200. And indeed it is 200. That's it. This is mostly memorizing. Let's look at them. Strengths, property of materials that need a large force to break them. Like for example, a boulder, it has a lot of strength since you're gonna need something really, really strong to break a whole boulder. Okay. Stiffness, property of materials that do not stretch or bend. So yeah, stiffness is something that can't be stretched or bent, like a rock. You can't stretch it, obviously. Elasticity is something that can be stretched, like a rubber band. Okay, property of material that go back to their original size and shape once the pulling force is removed. So when you stretch a rubber band, it's to its elastic limit and let go, it will return back to its original shape. Now for plasticity, property of material that stay permanently deformed after a pulling force is removed. So like a plastic bottle, if you crush it, it will stay deformed forever, like that. That's it. And for ductility, or ductility, whatever you want to call it, property of material that can be made into very thin wires. Metal is an example. Brittleness, property of material that breaks suddenly just after the elastic limit. If you put it past the elastic limit, they will break immediately. like glass. Alright? A string, one minute. A string balance is calibrated when it is at rest. It is then taken into a lift when and the 2 kilogram mass is suspended from it. Okay, 1 minute before we continue. As the lift starts moving upward, the spring balance reads 25 Newton for a few seconds. 25 Newton for a few seconds. Make sure to measure the mass. 20 kilogram. It's 25 Newton for a few seconds. Next, it reads 20 Newton. Then 15 Newton for a few seconds. Finally, it reads 20 Newton. Now, what's happening here, before anything, we have the mass and the force, right? Since the force is directly proportional to the acceleration, if force doubles, acceleration doubles. Force halves, acceleration halves. Okay, just keep that in mind. Now, let's read the steps exactly from step 1 till step 5. From number 1, the lift is initially at rest. They gave us this. So of course, first thing, it is at rest, already at rest. All right, it says initially at rest. All right, so that's step 1. Step 2 is the lift is accelerating. Okay, now when we drop the 20 kilogram mass from the spring balance, the lift starts moving upward. So it reads 25 newtons for a few seconds. Then it reads what's it called? Then it reads 20 Newton. Okay, so it started as 25 Newton, then to 20 Newton. That means it's accelerating. Okay, for the third one, the lift is moving uniformly. Now it's saying 15 Newton for a few seconds. Now it's moving for 15 Newton for a few seconds. For those few seconds, it's moving uniformly. Got it? By the way, if you're asking why it accelerated since force is less, let me just erase this. Look, when force decreases, when there's less force, there's more acceleration. Because remember, when there's zero net force, 1 minute. Yeah, so when zero net force, there is acceleration, right? Because in zero net force, like in Newton's first law, it says an object will move constantly or remain at rest unless an object is acted by a force, unless a force acts on that object. So since the force is 0, it can accelerate. Wait, never mind, guys. Force and acceleration, forgot, they're directly proportional. Silly me. Sorry guys. Forget the part about force decreases, acceleration increases. They're directly proportional, okay? I really apologize for that. Anyways, so it's 25 Newton for a few seconds, then it reads 20 Newton. So it's accelerating from 25 to 20 Newton, okay? Then when it reaches 15 Newtons for a few seconds, in that few seconds, it's moving uniformly, okay? Wait, what? Okay, I did something wrong here. It was at rest, so there was 0 Newton. And then the spring balance reads 25 Newton for a few seconds. Now, it is initially at rest, that's when it's 0 Newton. Then second is left is accelerating. So 0 Newton to 25 Newton, it's accelerating. That's the part where it's accelerating. I messed up. So, yeah. So that part is accelerating. Now we go to step 3. The left is moving uniformly. Now it's at constant speed, right? It's 20 Newton. Then it reaches 15 Newton for a few seconds. So when it's new to 20 Newton, it's moving uniformly at constant speed. But then when then it decelerates, number 4, the lift is decelerating. It reaches from 20 Newton to 15 Newton. So for a few seconds. So it's decelerating from 20 to 15. And then for the last one, the lift stops. Finally, it reaches 20 Newton. You got it? So at the end, it stops at that force. So yeah, that's it. So let's recap. It's initially at rest, then it accelerates from going from 0 Newton to 25 Newton. Then what's it called? It reaches 20 Newton. 20 Newton, that's uniformly, it's moving uniformly. Then 20 Newton to 15 Newton, it's decelerating. And then at the end, it reaches a final force, so the lift stops. That's it. Question 19. The International Space Station, ISS, is a manned satellite going around the Earth in a circular orbit. Select the correct free body diagram for a ball inside the ISS. Okay, for this one, it's logic. Since it's in space, it's a satellite in space, the only thing that's there is weight. There's no other force, there's no air resistance because there's no air. No gravity is weight, so it's that's the only force acting on it. There's no normal push or anything. It's in space, so the only thing there is weight. Okay, that's logic. Why the terminal speed of a parachuter is lower than the parachute when the parachute opens than when it does not open? This is also logic. So it's asking, why the parachuter when it's 1 minute? Why does the parachuter when it's in this state, when he has the open parachute, has lower terminal velocity than the one there's no parachute, like with no parachute open? So they're asking why this terminal velocity is lower than this, which has higher terminal velocity. Now, obviously, because there's air resistance now acting on the skydiver. Air resistance is here. It's affecting it, so the skydiver is decreasing its speed, which is decelerating. And when it decelerates, that's not terminal velocity. Terminal velocity is when it's constant velocity. And here, the skydiver is in constant velocity before you open the parachute. Alright? So, as it said here, air resistance exerted on the open parachute is larger. So, there is air resistance on the parachuter, since there is more surface area on the parachute than the one with no parachute, which has nothing to slow him down. Okay? That's why. Again, logic. Choose the correct answers to complete the sentences below. Provided the stretching force does not extend the spring beyond its elastic limit, the extension of the spring is directly proportional to the stretching force. This statement is known as Hooke's law. Yeah, basically, let me just quickly explain. Let's write the rule. Force equals spring constant delta L, K delta L. Now they're saying that the extension of the spring is directly proportional to the stretching force. Yeah, the stretching force. Remember, the force is directly proportional to the extension, like all of them. That's why we divided them. So force is always directly proportional to L, and K is inversely proportional to L. Okay. So when you read this is just a statement to memorize. When the force is directly proportional to the extension, it's known as Hooke's law. Okay, which is, for the last time, F equals K delta L. Memorize this. This is very, very, very important. Okay. Alright, guys. Thank you, and I wish you the best of luck in the exam. I hope you understood. Sorry for the confusion in that one question. Just listen to the way I summarize it and ignore when I was just messing up. Okay? Wish you the best of luck, guys. Thank you.